So that was a pre-pruning. Now let's talk about the post-pruning in this slide and onward. So in post-pruning, you build your decision tree in full scale, okay, all the way to the end, to the bottom. And then after that, you prune it, you cut some branches, right? So that's how it works in post-pruning. There are many post-pruning methods, and as I said, people use post-pruning more often than pre-pruning. So there are many post-pruning methods, but these two are quite famous. So in this chapter, you're gonna study these two post-pruning methods, such as reduced error pruning and the subtree replacement. Each of these will be studied in this chapter. Okay, the first post-pruning method we're gonna discuss here is called the reduced error pruning. So in reduced error pruning, you split your training data into training data and validation data. So in reduced error pruning, we have another data set called the validation data, which will be used later here. So okay, after that, you construct your decision tree in full all the way to the end, okay, and consider each node for pruning. So you consider a decision tree like this. You construct a decision tree like this, okay, and then each node here, this one and this one, is the possible node for pruning, okay. By the way, these are leaf node. These are class values, okay, so these are not for pruning. These are simple class values, okay. You don't prune these, okay. So in this particular decision tree, we may prune this node or this node, okay. So pruning here means removing the subtree at the node, make it leaf, and assign the most common class at that node. So for example, pruning this node means this part is gone, okay, and it is replaced by a single most common class value. Again, pruning this node means this part is gone and replaced by the most common class value of this data. Okay, that's the definition of pruning node here. Okay, then you have to decide whether you're gonna prune this node or not, okay. Similarly, you have to decide whether you're gonna prune this node or not, right? How do you do that? So, okay, let's begin with this one. So you wanna prune this node or not? The way we do this is, okay, you test the performance of decision tree, the original decision tree, using validation data. Okay, so using validation data, you test the accuracy, okay, of this decision tree without pruning, okay, and then you prune this, okay, and this part is replaced by a single common class value, okay, and then this pruned decision tree is evaluated using validation data. So using validation data, you test the accuracy of original data, and then using same validation data, you evaluate the performance of pruned decision tree. Okay, that's how it works. So if this pruned data shows better performance, then you go ahead and prune this node. Okay, this is replaced by class value. Otherwise means the original decision tree shows better performance than the pruned decision tree. Then you don't do it, okay? Just leave it as is, okay? So that's how it works. So same thing goes here. You want to prune this node or not, then again, you compute the accuracy of the original decision tree using validation data. Okay, this time you use validation data, and then you prune this. That means this part is replaced by a single class value. Okay, and then again this resulting decision tree. Okay, pruned decision tree is evaluated using validation data. So again, compare the performance between these two decision tree, and if this pruning improved the accuracy performance, then you go ahead and prune this node, okay? So that's how it works. So you repeat this for every node, okay? And you have to check whether you're gonna prune this node or not for every node in the decision tree. So finally, if for every node, again, you do this testing, okay, whether you're gonna remove or prune or not. And so when you actually prune node, you begin with the node which improves the decision tree the most, okay? So you begin with the node which improves the accuracy the most, okay? And then you move on to the next one. Okay, so keep going like this until pruning actually degrade the performance of decision tree, okay? So that's the process of reduced error pruning. The second post-pruning method is called a subtree replacement. So this placement has some similarity with reduced error pruning. So in reduced error pruning, you prune a node only if pruning improves the performance of decision tree, right? So same thing happens here in subtree replacement. So for each node, again, you prune the node only if the pruning improves the performance of decision tree. Okay, so these are the similarity between reduced error pruning and the subtree replacement. Then what is the difference between these two? The difference is in reduced error pruning, when you evaluate the performance of decision tree, you use the validation data set to test the performance of decision tree, right? But in subtree replacement, we do not have validation data. Actually, we use estimate of data to evaluate the performance of decision tree. So that's the difference between these two, okay? Reduced error pruning uses validation data to test the performance of decision tree. Subtree replacement uses error estimate to test the performance of decision tree. Okay, these are the difference. Okay, some similarities and some dissimilarities. So basically what you do in subtree replacement is, so for each node, for example, you have a decision tree. Okay, you construct a decision tree like this. Then for each node here, okay, for each node, this, okay. For each node, you actually estimate the error of the node before pruning actually. So for example, for this node, you estimate the error of node for the future actually, okay. You estimate the error of this node, okay, without pruning. And then in second step, you assume this node is removed, okay, removed, and so this is removed, and this is replaced by a single class label, okay. So in that case, you again estimate the the size of error, okay, in this pruned decision tree, okay. So you compare these two, the estimate of error before pruning and the estimate of error after pruning, okay. So you compare these two and you prune it. If the pruning actually decreases the estimate error, then you prune it, okay. Otherwise, if the pruning actually increases error or equal to the equal, then you do not prune, okay. So that's the basic idea of subtree replacement. So you repeat this process for each node. So that's subtree replacement. When you run subtree replacement, you begin with the bottom node, lowest level node first. You begin with this one, this one. Okay, so after these are done, you work on these node. Okay, and so you work. So this is bottom up approach. You begin with the lowest level node and move upward. Okay, so that's subtree replacement. You for each node you estimate the error, okay, and based on the value of estimate error, okay, you may, if the pruning decreases error, you prune it, okay. So this picture shows an example of applying a subtree replacement. So as I said in the previous slide, a subtree replacement is a bottom-up approach. So you begin with the lowest level node first. So in this original decision tree, you begin with this and this, right? So you work on this one first, health plan contributions. So you have to decide whether you're going to replace this one, okay, by a single class label value, okay. So what you do is, again, you estimate the error of this original tree, okay, and then you assume this is removed, okay, this is removed and replaced by a class label, okay, majority class label, and then again you estimate the error again for this pruned tree, okay. So you compare these two, and if the pruned tree shows smaller estimate of error, then you go ahead and eliminate this tree, okay. That's how it works. So you work on this one and you work on this one. Again, this is bottom up approach, and then you work on this one and this one, etc. Okay. So in this case, maybe this is possible. This whole thing is replaced by a single class label, bad. So this is actually the majority class value of this subtrees. Okay, so this whole thing can be replaced by bad. Again, depending on the value of estimate. Okay. The subtree replacement method uses the estimate of error to decide whether or not to prune the node. And if the pruning reduces the estimated error, then we prune the node, right? That's the basic idea of subtree replacement method. And then when it comes to the error, there are two type of errors. The first one is error on the training data, and the second one is the error on test data. So as I said previously, the error on training data is not important actually, and what really matters is the error on test data. So in this method, we focus on the error on test data. By the way, if you run this method, the subtree replacement method, based on training error, then what's going to happen is probably you don't prune any node in your decision tree because when you build your decision tree, you use training data. So decision tree is based on training data. So you can say a decision tree is kind of explaining, okay, it's explaining the training data. So if you remove any node from decision tree, okay, and again, decision tree is based on training data, then probably you're gonna increase the error of training data, okay? So because of that, if you run this method based on estimate of training error, then probably you don't prune any node in the decision tree. So anyway, that's why we used estimate of test data. Okay. So in C 4.5 decision tree method, so anyway, now our goal is to estimate the error on test data. But the problem is test data is the data of future. Okay, these are the data we haven't seen yet. Okay, this is different from training data. So the question is, how do you estimate the error of future data? Okay, test data is the data in the future. Okay, that is the question. So actually, we cannot exactly compute the size of error for future data, the test data, right? But instead, what we can do is we are able to compute the range of error, okay, range of error on test data. Even though we cannot compute exact value, exact size of error, we are able to compute the range of error on test data, okay? So that's what I said here. We derive confidence interval of test error, okay, from training data. So using training data, even though we cannot compute exact number, single value, we are able to derive confidence interval, the range of test error. Okay, we can do it. Then use this range confidence interval for pruning. Okay, so that's the method used in the C 4.5 decision tree. Okay. The basic idea of this one here, the deriving confidence interval, the deriving the range of error. Okay. To do that, we use a Bernoulli process-based method. I'm going to explain this in next slide. So basic idea is we assume each data instance, okay, each data instance in training data is kind of a Bernoulli trial, okay. So each data is independent Bernoulli trial, okay. So that's basic assumption of the method, okay, to derive the confidence interval. So I'm going to explain this, the detail of this method in the next slide. Okay, suppose we have a decision tree like this, and also you're gonna prune this node, which contains 4 bad and 2 good. So pruning this node means this is replaced by class value bad, because bad is majority value here. Okay, so in that case, then what is the error rate? Okay, can we estimate the error rate of pruning this node? So the error of training data is very simple because all these data are the training data. Okay, again, decision tree uses training data. So the training data of this node is okay because this thing is now replaced by bad. So we have 2 error. Okay, good is error, so these 2 are error, right? So we have 2 out of 6. 2 out of 6 is error. So error rate of training data is actually 2 out of 6, which is 0.33. Okay. So let's say this error rate is f. We're gonna use f value in next slide. Okay. Anyway, so computing error rate on training data is easy. Okay, right here. Then how about the error rate on test data? It's tricky actually, because a test data is the data we haven't seen yet. Okay, it's the data in the future. So how can you estimate? How can you compute the error rate on test data? So that's tricky. Before we compute the we estimate the error on test data. You're gonna transform this problem into this problem. Okay, then what is this problem? Suppose we have this strange looking dice. Okay, and then you are interested in computing the probability of landing this side. Let's say this is good side. Okay, you're gonna compute the probability of landing good side here. Okay, suppose that is our goal. Okay, then yeah, I think definitely we cannot solve this problem by using analytical method. Okay, I don't think we can come up with a very fancy formula which explains this dice. So okay, so the analytical method is almost impossible. Then how can we compute the probability of landing good side? Okay, from this dice. Okay, then you can compute this by using experiment. So let's say you roll this dice 6 times. Okay, then we have seen 2 good. Okay, and we have seen 4 bad. Okay, then we are able to compute the estimate. Okay, of this true bad. Estimate of the probability of landing good. Okay, so out of this experimental result, we can estimate the probability of landing good. So this problem is now is very similar to the problem like this. Okay, next slide we're gonna give you more detailed explanation of this procedure of computing error rate on test data. Okay, now let's compute the error rate of test data. Suppose Q is the true error rate of test data. So Q is the value we are looking for. You're going to estimate. So Q is not known. And in the rolling dice case in previous slide, then Q is the probability of landing good, right? Okay, so basic idea here is in the node we're gonna prune. There are multiple train data, and each train data. Okay, each train data is assumed to be an independent Bernoulli trial with probability Q. Okay. So there are multiple train data in the node, and each train data is an independent Bernoulli trial with probability Q. That's the basic assumption. Okay, so that trial is repeated. Okay, so let's say there are like 10 train data in the node. Then this Bernoulli trial is repeated 10 times. Okay, that's the basic assumption. Okay, that's the basic idea of this method. So by definition, the error in this case means the class level is good. So in our particular example, if you look at the previous slide, the majority class was bad. So that means if the class level of data is good, then that is the error, right? That's simple. So anyway, we assumed that each data is an independent Bernoulli trial with probability Q. So then, so we have a multiple train data in the node. Okay, so let's say let's define the error rate. Okay, in the node. So there are, let's say there are capital N number of data. So N is number of data in the node. Okay, and let's say F is the number of error. Okay, so in this particular example, its number of class level is good. I told you here. Okay. So the error rate of the node in the error rate of that particular node is, this is number of failure divided by number of trial. In other words, this is the number of class level good divided by number of data in the node, right? So this is the definition of error rate, F. Okay. So this actually is the Bernoulli distribution, okay? And for large number of n, if n goes very high, in n goes very large number, then f follows a normal distribution due to the law of large numbers, okay? So if n becomes very large, very big, okay, then the f follows Gaussian distribution, okay, normal distribution. This is called law of large numbers. And I said a shaky assumption in sheet 4.5. That means, so f follows Gaussian distribution when n is very large. Okay, f follows Gaussian distribution when n is very large. But in a decision tree, usually this n is number of data in a particular node. Okay, so in many cases, the number of data in the node is not very big. So this assumption is a little shaky, okay, in decision tree. So, but in practice, it works pretty well in practice. So we just use this assumption, okay, assuming this f follows normal distribution, and works pretty good, okay. So now f follows normal distribution like this, okay, and in this normal distribution, its mean value is q, and its variance is given as q times 1 minus q divided by n. This is the variance of this Gaussian distribution. So in a previous slide, we could compute the f value, which is the error rate of training data, right? So using this f value, can we somehow compute the value of q, which is the true error rate in the test data, okay? So can we somehow compute the value of q from f, or at least can we compute the range of q value using f? Okay, that's the question here, okay? So from the value of q, can we somehow estimate the range of q value? So for example, do we have something like this, okay? It says with the confidence 90%, with confidence probability 90% or confidence 90%, we can say q value is between A and B, okay? Do we have something like this, okay? So for example here, this is f, and q belongs to this range with the 90% confidence, something like that, okay? So if you look at this picture here, so we know the value of f value, so f is given, we know the f value, okay? And the q value, which is true error rate, okay? These are not identical, but these are strongly related, right? So this is the q value, and this is f value. So we know the f value. So q value is very much likely to be close to f, okay? Because they are very similar, not identical though, okay? It's very similar. So this is very much likely to happen, okay? But here in this case, this is q value. So q value is very far away from f. This is very less likely to happen, right? So this is very much likely to happen, and this is very, very unlikely to happen, right? So can we somehow to have something like this? Okay, so the range of Q is between this and this with the accuracy 90% or something. Okay, so that's our goal. So in a previous slide, I said to estimate the true error rate of test data Q, we need a formula something like this. Okay, the probability that the variable is greater than minus z and less than z is c. We need something like this. And actually, we do have this formula in standard Gaussian distribution. So if you remember the definition of standard Gaussian distribution, by the way, a standard Gaussian distribution is Gaussian distribution where its mean value is 0 and the variance is 1. So that Gaussian distribution is called a standard Gaussian distribution. So in a standard Gaussian distribution, we do have this probability. For example, if x is greater than minus 1.65 and less than 1.65, its probability is 90%. Okay, you can compute this out of this table. Okay, so we do have this formula. Okay, from standard Gaussian distribution. So you can make use of this formula to compute the range of Q, which is the true error rate of test data. Okay, now we're gonna use the property of standard Gaussian distribution, which I explained in last slide. You know, the probability the x is greater than minus z and less than z is c, right? Yeah, something like this. Okay. Then again, to use this should be should follow a standard Gaussian distribution, which means this guy's mean value is 0 and its variance is 1, right? So to do that, to do that, you have to change original f value. Okay, to remember f value follows Gaussian distribution. Okay, this Gaussian distribution, and but this is not standard yet. Okay, so we have to change this f variable. Okay, to a standard Gaussian distribution variable. Okay, so we change original f to this form. Okay, so this is the way we change variable to standard Gaussian distribution form. Okay, so by doing so, this its mean is 0 and the variance is 1. Okay. So now f is changed to this one. Okay, so you plug this in here. So x is now this one, and from the confidence level C, we have this formula. Okay. So if you look at this, f is given. We know that this is a training error. You know this one. Okay, q, we don't know q. We're gonna estimate q. Okay, z is given from the Gaussian distribution, standard Gaussian distribution table. Okay, this is determined by C, confidence level. Okay, for example, the C is 90%. This is 1.69 or something. Okay, so if the confidence level is given, this is given, this is given. Okay, n is number of data which is given, f is given. So Q is the value we're gonna estimate, right? So you solve this one, this formula, or this formula, this one here. Okay, what I'm saying is minus z equals, we are computing boundary of this. Okay, boundary of this one. Again, we are computing the boundary of q value. So we put minus equal here and compute this for q value, and you put equal here and solve this for q value. Okay. So by doing so, q equals, okay? Q equals this. So a little complicated, but anyways, Q is this. Again, we know F value, we know N value. N is number of data in the node. We're gonna prune. And G is determined by the confidence level C, okay? So if N, F, blah, blah, okay? So a little complicated, but we are able to compute this one, okay? You can compute Q value. And because there is plus minus here, okay, we are computing interval, so we give maximum value here plus, okay. So that's the bound maximum value of Q. So in the previous slide, we compute the Q value, actually the boundary of Q value, okay, maximum boundary of Q value, which is also given here. Notice that this is plus only. In previous slide, there is plus minus here, but we are interested in maximum boundary, maximum amount of error. Okay, so we use plus here. Okay, so this is the maximum upper bound, maximum boundary of true error in test data. Okay, so F is a training error, okay, it's training error I mentioned, and N is the number of data in the node, okay, you want to prune, and Z is it's determined by the confidence level. If C is 25%, then Z is 0.69. You can compute Z from confidence level, so that means we are able to compute this value, which is the maximum boundary of error rate in test data. Okay, so you can use this. And finally, if a certain node has a multiple branch, okay, then we compute this error estimate for each branch, okay, and then we do a weighted average of estimate to compute the error estimate of the node. I'm going to explain this in next slide. Okay, this is the final example of computing error estimate on test data. So suppose this we have a decision tree and we have attribute, and it has 3 branches, and each branch has this leaf node. Okay. And then, as we have seen in the previous slide, we can compute the error boundary for this one, right? So for this one, if you compute the error boundary using the formula in the previous slide, the error boundary is 0.47, and F is training error here, right? So 2 out of 6 is training error. So this 0.33 is training error. For this one, if you compute the error boundary, again using the formula in previous slide, is 0.72, and again training error is 0.5. For this one, error boundary is 0.47, training error is this, okay. So if you combine these 3, okay, using weighted average, okay, then it's gonna be 0.51, all right. And then finally, we have to make decision whether you're gonna prune this node or not. We have another attribute, we have another error estimate here. So what happens here is you simply remove this part, okay, remove this part, and this whole part is replaced by a single class value, okay. It's gonna be this whole data is combined. Let's say in that case we have 451. We have a 9 bad, okay, 414, and we're gonna have 5 good, okay. We have 5 bad and 9 bad and 5 good, right? So majority is bad, 9 bad, majority is bad. So this whole thing is replaced by bad, okay? So in that case, we want to have something like this: 9 bad and 5 good. Okay, so for this particular distribution, we can compute the error boundary. Okay, that is the error boundary here. Okay, so this error boundary, this one, is the case where we combine these three and we have 9 bad and 5 good. Okay, so this is the case. Okay, this is the case where every data is combined into one distribution. Okay, so in this case, without pruning, this is error boundary without pruning. Okay, and this one here is error boundary with pruning. Okay, let me repeat. The error estimate, this one is we don't prune any node. Okay, so this is the error estimate. Error estimate of test data without pruning. Okay, and this is the error estimate with pruning. Okay, so this is the case where whole thing is gone and replaced by 9 bad, 5 good. Okay, so in that case, error boundary is 0.46. Okay, so this is less than this, right? So that means this is better. Okay, this is better. So that means you kill this and the whole thing is replaced by a single class value, which is bad, BAD. Okay, so that's how it works in the subtree replacement. This final slide is about changing decision trees to rules. Let's say we have a decision tree like this. Then if you find a path from root to leaf, for example, outlook sunny, humidity high, no, right? For every path like this, you have a rule, if-then rule. Okay, so for example here, outlook is sunny and humidity is high, then class value is no, right? That's exactly what happens here. So outlook is sunny and humidity is high, then play tennis is no. For this one, like outlook is rain and wind is weak, then play tennis is yes, right? So outlook is rain and the wind is weak, then play tennis is yes. So for every path from root to leaf, we do have one if-then rule. Okay, so we have 1, 2, 3, 4, 5 path. So we have 5 if-then rules. Okay, so we can change a decision tree to rules like this. So another advantage of changing decision trees to rule is we can use this as a tool for post-pruning. The way it works is like this. So you change decision tree to rules like this. Okay, that's easy, straightforward. And then you randomly kill some condition here. Let's say you kill this one or this one, etc. Okay, and then you kill these conditions randomly. Okay, and then test the performance of this using validation data set. So this is very similar to reduced error pruning. Okay, but the only difference here is in this case you change decision tree to rules. Okay, and then randomly kill some conditions in if part. Okay, and then test the performance using validation data set. Okay, that's the only difference, but it's quite similar to reduced error pruning. So one pass means one rule like this, and it can be used for post pruning using validation data set.